Okay, I will not be too original at first because I want to thank also the organizers for giving me the opportunity to visit this wonderful place and to participate in this nice conference. What I'm going to tell you is work done recently in collaboration with various combinations of these people, and it relates to twisted matrix models. I will tell you some recent results we obtained and also what are the future prospects of this topic. So first I have to define what these twisted matrix models are, which probably many don't know. It's a class of matrix models which in the large N limit are claimed to be equivalent to the large N lattice field theories at infinite volume. So here the words lattice and the words large N and at infinite volume, that's the crucial thing. So there is a common denominator of these theories that they have in their formulation, they involve some fluxes. So this is something characteristic of all these models. And these theories have also been considered as regulators of non-commutative field theories. So the study also can be interesting to understand non-perturbative features of these theories. As a matter of fact, despite the fact that this is lattice theories, of course, if this equivalence takes place at all values of the coupling, it will survive also in the continuity. So let me start with the oldest of this class of models, which is pretty old, which is the TEK model. And it's a model of matrices, because it's a matrix model. How many matrices? Just the same as the number of dimensions, and they are all unitary matrices. So these integrals are over the Haar measure. The action is this, which looks just like Wilson action, with one difference, that there is no spatial label. And in addition, there is these factors here, which are just elements of the center of the group. Therefore, I mean, in principle, they are characterized by these integer numbers, which is this is called the twist tensor, and they are just integers defined modulo n. Okay. So, how do you get to this model? Essentially, what you do is to formulate your lattice gauge theory in a finite volume with twisted boundary conditions, and then you reduce the volume to 1 point. Of course, you don't need to reduce it to 1 point. You can just keep your box. So L is the size of this box. If you take L equal 1, then you have this model that I'm describing here. But frequently, I will be using bigger sizes. So it's some kind of volume reduction, which is volume independence is this thing that is here. So the claim is stated here that this theory, this model, is equivalent to the infinite volume large N Yammer's theory. Okay, but this is the crucial thing, which I will spend a big part indicating, which is for an adequate choice of the twist tensor, because there are a bunch of freedom, because that's a freedom that we have in defining. So the crucial thing is how to choose this twist tensor. So first, we have to go back to what the motivation that these theories, this equivalence that I'm telling you, and this goes back to the work of Eguchi and Kawai, where they showed that these two theories are equivalent, provided that the center symmetry group, which is this transformation of the lattice variables, which you can see that leaves the action invariant, is also respected by the vacuum, that is not spontaneously broken. That's the assumption of this theory. So it has to do with that. Later, we studied, because the equivalence, if it has to be true at all scales, it also has to be true in perturbation theory. So that gives you some insight about these values of n. So if you study perturbation theory, you see that not all choices are good. And that restricts the values that you can take for these twist tensors. In particular, it tells you that your twist tensor has to be orthogonal and irreducible. I'm not going to tell you what orthogonal and irreducible, because I will restrict to a class which is simpler, and then it will be simple to understand. For example, in particular, in 4 dimensions, you can take a simple choice which satisfies this constraint, which is given having all the twist tensors to be in absolute value the same. But to do that, you need to have your n of the group to be the square of an integer. So remember, L hat is going to be the square root of n. It will appear repeatedly. So now you have only one parameter instead of n mu nu. So now the question is how to choose the flux Q to ensure that you have center symmetry. But in addition, there is an important thing, how to make the corrections small. For practical purposes, that's very important, because we are not going to, if you do numerical thing, you're not going to get the n equal infinity, okay? So if you're not an infinity, what errors do you make? So we come to the next point. So if you analyze this model at finite n, how does it differ from the large n theory? Well, in 2 points. There are 2 aspects. The first one has to do with the structure of the propagators. You can see this in perturbation theory, and it tells you that n plays the role as effective volume. So you're sort of introducing space inside the group in this particular way, in this. So the propagators look as if your lattice would be larger by a factor square root of n. If you are in the TK model, the lattice was 1 point. But still, your effective lattice is square root of n. No? That dictates also how to use this model, because if you want to study a quantity which has some extent, you better take square root of n much bigger than this, because otherwise you'll be subject to this finite size correction. So that's always used when applying this model in practice. The second aspect is that, of course, planar diagrams are 0 in the large n limit. However, if you take n finite, they are non-zero. So that's the other error you make. And this part of the error is very much dependent on k, the flux, remember. K bar will appear repeatedly in what I will tell, which is just the inverse of k modulo n. So it's another integer, and it will also play a role. So let's see, and this is a calculation we did last year, to compute Wilson loops in a theory where you still keep L, you still make it not necessarily a twisted model, but it's a particular case, because L equal 1 is the twisted model, any value of n and any value of the flux, and compute Wilson loops and see whether it's true. Of course it's true, because I made a proof long time ago, but we want to know how the corrections look like, okay? So, in particular, we're interested in the effect of these non-planar diagrams, okay? So, these non-planar diagrams contribute to second order in perturbation theory. They don't contribute to leading order. So, to leading order is just the effect of finite size. But beyond that, they contribute, in this way, where am I? Here, okay. The contribution to the coefficient on the lambda square is proportional to 1 over the volume, the effective volume, so 1 over n squared, okay, times a coefficient which depends on k, n, and l. But how does it depend? Okay, we see it here. I mean, this is done for a lot of cases. We did the calculation for many values of k, n, l. So, and they're all plotted here. It's an analytic calculation, okay? So all these numbers have no errors, okay? And what you see is that there's some kind of universal behavior. The coefficient can be very different from one point to other, because the coefficient here is very small, the coefficient here is very large, and I'm not drawing the ones that are here because they're even higher. So it's very important for the corrections that you choose the right value of k, okay? But in any case, this thing goes to 0 for any choice when n goes to infinity, but the rate can be very important, okay? So that's the first message, and we can investigate further and understand the leading behavior of this. And this has to do with this quantity here, which will appear later. This quantity is a number which is the minimum of the product of n being an integer going from 1 to square root of n, times this quantity here, which is this same integer, times k bar divided by square root of n, and this double bar means distance to the nearest integer. So it's 1.2 is 0.2. 0.8 is 0.2. The distance to the nearest integer, okay? So you compute this, and you subtract the integer part, and you... Okay, so here I am comparing the previous plot, so with this function of this single variable. And you see it captures everything, even the dips and the heights of everything. So this is the quantity that controls, and we will talk about this later. So we know it's very good that we identified the relevant object. Okay. What happens, I mean, now we have examined perturbation theory. There everything works, but of course, I told you before, we have to have that at all values it should be equivalent. So what about intermediate coupling? Here, the only thing you can do is just to simulate and see if the symmetry is broken. Then the proof, which is non-perturbative, breaks down. So it could be wrong. So, and in fact, some people did this analysis, and they found results in which there were signs, actually, that the symmetry was broken. So then the whole thing collapses, and the theories are not really equivalent. The model is not equivalent. And that's the moment when I started looking back at this model, which I had worked many years after. So I came back at 2010, when these negative results. And the first thing we realized with my old colleague, Okawa, which was that this problem only took place when the ratio of this flux to the square root of n, or k bar over square, was smaller than 0.1. Beyond this point, there's no experiment, there's no simulation which has shown any sign of symmetry breaking. Furthermore, we have reached to very high values of n. Okay, but still, we wanted to see whether it works or not. And now we are in a very good situation, because we are comparing a model with something that we can do also on the lattice. We can take the large N limit the way that Biagio is doing by extrapolating from results at finite N. And it's a lattice theory, so it's very easy to do the comparison. So we just have to compute the same things, Wilson loops. And we did that experiment, doing exactly the same thing. We did extrapolation with periodic boundary conditions, large lattices, and various values of N, here from 8 to 16. And we also did the model with one point, only one simulation, no volume, and N very large, because we don't have volume, we can afford to have a very large N, right? So, and this is the comparison. If you look, this is the plaquette, R equal 1 is 1 by 1, and this is the 4 by 4 loop, at 2 values of the coupling. And you see, the errors in the plaquette are of the order of 2 parts in 10 to the 5, okay? So the agreement is not just qualitative, it's just quantitative to the level of the errors, which in this quantity, they are particularly small. And in the case of the 4 by 4 loop, they are also compatible with the errors, this time of the order of a few per mil, okay? So that passes the test. In addition, of course, we're interested in the lattice is just an instrument, we want the continuum limit. So we also studied something that is in the continuum, in particular the string tension. So, but not to bias the thing, we did it all ourselves with the same techniques. I mean, we used the same method to extract the string tension from Wilson loops, but we did it in 2 different ways. I mean, two different theories. One is a theory where there's space, and of course cannot be too large, because we are limited because the space is large, and we extrapolated to the value to n goes to infinity with 1 over n squared and now 1 over n to the 4 corrections, and we got this number. If you do the same thing with the same observables with this theory, you get with n, which is much larger, you get this number. So within 1%, we also agree at that level. Okay. So this is a different story, which, as a matter of fact, is a little bit different, but sometimes to learn about this, you have to go to a even simpler system, and then maybe something that you learn from that can be extrapolated. This is a study instead of 4 dimensions, this is T2 times R. So, and here, the setting is different. The setting is that in space is a 2 torus, and there is flux. There is one parameter, which is the flux, which is K, which is here. We also allow for this torus to be, it can be done in the continuum. Many things can be done in the continuum. In the end, we will do lattice calculations, but all these things is basically in the continuum. And this is the size of the torus. This is n. And actually, this setting is important because, as I told you before, these theories have been used as regulators of the non-commutative field theories. And actually, this setting has been studied in the first decade of the century by a bunch of people, where they actually looked at that, because these theories are exactly, they say Morita dual, but it means the same, to non-commutative field theories in a non-commutative torus of size Ln. We see again these 2 things coming together, and with a non-commutativity parameter, which is a rational number, and it's given by k bar divided by n. Okay, so these are exactly non-commutative field theories. Actually, I wrote the first non-commutative action before Kohn and company using the continuum limit of these theories. Okay, so what are the observables? The observables are the energies, the vacuum, the minimum energies in each electric flux sector. I'm not going to explain what is electric flux sector here, but they are different. The Hilbert space has a symmetry, which is the center symmetry, and you can classify the states according to electric fluxes. And these are the energies. Of course, it depends on the sector, it depends on K, on N, on L, and of course, on lambda, the coupling constant. But because of dimensional reasons, it can all be traded into a dimensionless function of dimensionless variables, which is this one here, where the dimensionless variable x, which is the only real variable, is just the product of lambda, n, and l. We are in 2 + 1 dimensions, so this is dimensionless, okay? Okay, what the people that did non-commutative activity here found is that these theories can have actually instabilities. They studied it from perturbation theory. And they found it can happen that these energies become zero at finite volume of the volume. So they start, in perturbation theory, the volume is very small, their perturbative calculation can be trusted, but then the perturbation theory tells you that there's going to be a singularity at some value of the coupling. When the box becomes a little bit large, then there will be a condensation, and that's interpreted as a condensation. It has to do something with the breaking of the global symmetry, okay? So what we did was just to study this on the lattice. I mean, we wrote several papers, 2 papers, but we are writing another one which will come out this year. And we did a lot of work because we studied n from 5 to 89, l from 1 to 28, x from 0.2 to 8, I mean, range of values. And summarizing something which is a long paper, because there are many, 50 pages or so. But the most important thing for what I'm going to tell you next is that there is a very simple formula which actually matches the results that we obtain numerically. And this very simple formula is the combination of the 2 things that you know from the theory, the behavior at very weak coupling, at very small volumes, and the behavior at very large volumes. At very small volumes, perturbation theory, as I told you before, is valid. So you can compute in perturbation theory, and we did, up to 1 loop. I mean, leading and next to leading order, and you compute what are the energies in perturbation theory. If the box is very large, then you have confinement, and then everything will be a string tension, will dominate the behavior of these things, and in addition, you can correct by the so-called Lusher term, which gives you the correction to that, to leading order. But if you combine the 2, which come from the 2 extremes, you get a formula which is a function of it's a polynomial. Well, it's not a polynomial because you are divided by x squared, but it has 4 coefficients, but they are fixed. These coefficients are essentially fixed, and these are the results, numerical results that we got. And each point here is a simulation at the different value of, well, this is fixed value of n and k, but we did all these numbers that I told you before, so there are many plots like this. But this is one to show, and these are the electric fluxes in each sector we measure for various values of x. What are the energies? And these are the dots. And these lines here are the results of this formula, where essentially there are no free parameters. Only the string tension you have, but it's been measured by other people, but you have leave some liberty here. I mean, it's not a fit. It's just to describe, I mean, it's not supposed to be correct. It's just supposed to that it captures really what happens. But this is important because you remember, if these things cross 0, then you have an instability. So you have a formula that tells you whether this will happen or not. And actually, when it tells you it's going to happen, it happens, okay? So, and since it reproduces the numbers, when these numbers don't touch 0, you don't have tachyonic instabilities. And that allows to do a study which allows to go beyond what you can compute, because you have a formula and then you explore the implications of the formula. And part of this thing was the master thesis of this guy, and also a published paper with him. And these are essentially the conclusions of this paper, is the fact, okay, what we want is that to have the minimum of all these energies as you scan over all electric fluxes, so that no one has a 0 value. I mean, so you want to bound them. No? And this is a function of Z min, which is the same quantity that appeared before, with one replacement that here is n instead of square root of n because we wanted to form 4 to 3 dimensions. Okay, that makes it. And then you can really think about how does this quantity behave and how can we bound. So if this value is bigger than 0.1, then there are no tachyonic instabilities. Then you have to study what does this mean. And then there is a collection of number theory results. As a matter of fact, this guy is a mathematician, but he was my student of master. And actually, the thing was that the conclusion is that there is a paper of 2 years ago that ensures that for almost all n, you can choose the flux in such a way that you avoid having tachyonic instabilities. To make this almost go, I mean to say for every n, there is a case such that no tachyonic instabilities is something that is a conjecture, which is called Zaremba conjecture, and it has not been proven, although many people think it's correct, but it has not been proven. Furthermore, it also tells you that there is an optimal choice, because you can make these minimal energies maximal, okay? And to do that, you have to choose n to be a Fibonacci number, and k, which will become equal to k bar, equal to Fibonacci minus 2, for example, 13 and 5, or 89 and 34. Okay, so that's the optimal choice. Actually, you do the simulation. Some of them we did a posteriori, and yeah, it worked. So it's like that. Well, it has a negative implication for another program having to do with non-commutative field theory, which is this work of Álvarez Gaumé and Barbón, where they say, okay, in non-commutative field theory, you want this theta parameter, this non-commutativity, is any real number. So, and these theories are just for rational values. So can we define the theory for irrational as a limit of rational numbers, and then they will be just normal theories with twisted boundary conditions? And the answer to this question we can give thanks to this, and the answer is yes, but only if this irrational belongs to a set which has zero measure. And it's actually, this is, for example, one case, it's related to the golden ratio, but it has a positive Hausdorff dimension, it's a kind of Cantor set. So that's the implication. So, okay, so what can be done? Well, we have I hope I convince you that this gives results that we have under control. If we choose properly K, that there are going to be no problems. We also have to change it to minimize the errors, and then we can compute. We have a model that achieves the possibility of reaching large n in a different way to the one that Biagio are doing, and they can have pros and cons, but I think it's worth pursuing. I'm not going to tell you about that because I don't have enough, but that's another continuum quantity that we computed. I think nobody has done before in the continuum limit. We can also study the meson spectrum and decay constants that we have done, and let me show you a few results. For example, this is the quantity I was not going to show. So that's the Pion mass as a function of the PCAC mass, essentially the quark mass, and you see the Pion mass square goes like this. It shows two things: first, chiral symmetry breaking. And second, that scaling is achieved because those two values correspond to different couplings. So we are close to the continuum enough so that we don't see that. You can look at the raw mass and see that the numbers more or less agree within errors for different couplings. So scaling is achieved and extrapolates linearly this time to some value in the chiral limit, which will be the raw mass in the chiral limit. We can also do F pi. And we can also do the rest of the spectrum. This program is not completed. I mean, we will have final results. We will give numbers, which will be the continuum limit of these masses of mesons in the large n limit. This is the comparison with the result obtained by Biagio Bali in another paper by the other technique. So, but you can do other things. You can, in principle, study. Well, that we also study, which is the gradient flow routing coupling. You can study these kind of things. Global spectrum is perhaps the most difficult thing, but clearly the chiral condensate. You can do finite temperature with a trick that was invented many years ago by Das and Kohut. And then, of course, you can do 2 and 3 dimensions. We are doing 3 I showed you, but 2 dimensions is also interesting because there are lots of problems in 2 dimensions. And we know the meson spectrum in 2 dimensions thanks to its top model. So we can compare, we can see how that gets. And of course, don't forget that it has an interest because it's also associated to non-commutative field theory. So the results can also be interpreted in this way. So we move to other, not much time, just other twisted matrix models. Okay, so a priori, this can also be done. I mean, this was a model that we dedicated all of the time to it, but we can add fermions and we can add bosons, matrix, and also we can also formulate non-gauge theories. This is the prescription. It's essentially creating a non-commutative field theory discretized, which will have the same Larchen limit as the one, because the proof of that it agrees in the Larchen limit does not depend on whether it's discretized or not. It's combinatorial. And you can also study Young Mills in the Venetiano limit, which it's possible with this method. So I don't know of other results that can study this. Maybe you know. I don't know. But anyway, here. And in principle, n equal 1 Susi Young Mills, I would have loved to say something about that because there have been many talks about that. But a priori it's feasible. We have, of course, the same problem of the phase, but still, we have generated some configurations with taking the absolute value. But anyway, that's it. Let me show you just something about the fundamental meson spectrum. This is the Pion mass as a function of M quark for a theory with 2 flavors. This theory has an infrared fixed point. It was pointed out by Biagio in his talk, where there is the theory is conformal. And it's not chiral, there is no chiral symmetry breaking, so it behaves very differently to the NF equals 0 case. And you see here that this is the quark mass, this is the Pion mass, and it behaves linearly. Perhaps it's more striking to see it here, because here I show the comparison of the ratio. Actually, this is incorrect, it's the other way around, but mass of the Pion divided by mass of the rho. This is with 2 flavors in the adjoint, and this is with 0 flavors in the adjoint. Here you have the chiral symmetry breaking, you see how it behaves, here you have the other. So this shows clearly that this theory is, at least at the level of this quantity, it behaves conformal invariant. Okay, and essentially, that's all that I have to tell you. We have results here, but I don't have time to show. So anyway, I will finish with the conclusions, which is a summary that you can read by yourself. Essentially, I hope I convince you that we have an instrument which is capable of doing things in the Larchen limit, many theories, and in a few years, maybe we can present results of something that has not been calculated previously. So thank you very much.
Questions?
Can you explain how finite temperature is here?
Okay. Well, I thought I had a very good idea because I decided, well, you can do it this way. And then I realized that that was written in a paper about 20 years earlier. So that's the idea of Das and Kogut. But, so it occurred to me independently. And you have to do asymmetric couplings. So even in a one-point box, of course, you have to test that. Even in a one-point box, you can make the lattice spacing in the time direction and in the space direction different. And even if you have same size in both, if you tune the parameters, in practice, you can make that the one direction is shorter and it corresponds to the temperature direction. And actually, you can do that nowadays, and you see that there is a sharp. But we didn't really, check that this happens clearly. There is an order parameter because this Polyakov loop, because I didn't have time to explain many things, but if you take the link to the power square root of n, this quantity plays the role of the Polyakov loop. It's also written in Das and Kogut. It's part of the story. So the trace of this quantity in perturbation theory becomes 1, okay? I mean, n. However, if you measure that strong coupling, you get 0. So it's going from u Zn to the power 4 to C square root of n to the power 4, which is the symmetry that remains in the weak coupling region. So actually the center symmetry is broken. But it's broken, but leaves a subgroup that is big enough so that the equivalence is maintained. So that's what acts as the order parameter. Yeah.
Over here. Your results for the pseudoscalar mass with 2 flavors of adjoint fermions, I'm trying to understand why the meson mass looked quite non-zero even at a vanishing value of the PCAC mass. So about 3 slides ago, if we want to go back.
Well, yeah, because this is meson spectrums in the fundamental. Okay, and so this is not the meson states where these mesons are adjoint quarks. These are mesons in the fundamental, which you can add because they are non-dynamical. The theory is in the Larsen limit, so you have dynamical quarks in the adjoint and non-dynamical quarks in the fundamental. So you can measure these mesons, have the same properties. However, the difference is that the configurations where you measure these mesons is done, of course, with dynamical fermions, but in the adjoint. So there is a parameter, because this is which is the mass of the adjoint. And only when this mass of the adjoint goes to 0, you get this result that you are saying. I mean, that should happen. So we are not really conformal. I mean, the conformal limit would be it should go to 0. But we are not there also. I mean, all these masses should go to 0 in the conformal limit. But for that, you have to tune the mass of the quark in the adjoint to 0. Otherwise, there is a breaking. So that's the reason. That's my explanation.
Maybe I can follow up with a quick clarification. Is the PCAC mass on the horizontal axis of that plot then the fundamental mass or the adjoint mass or both?
That was PCAC in the fundamental. So these mesons are in the fundamental.
So I would still expect a 0 of massless pion and the limit of 0 fundamental mass. So there's something I don't understand and I'll have to discuss with you.
Okay, we can talk later.
Comment/question. The obstruction that we get when we do the simulations at large N have to do with the topological freeze out, essentially. I mean, the topology as we increase N gets stuck in a topological sector. And that affects the ergodicity of your simulation. In your setup, do you get any remnant of that, or is the topology under control? Or
I cannot really answer. I just can tell you that, of course, all the simulations we did previously, they cover the same values of B, and we computed the Wilson loops. And of course, it doesn't tell you that all quantities will go, but all the quantities that we measured on the lattice were at the same values of the coupling, and we found that they went right to the correct, and we didn't have very long thermalization, not thermalization, but autocorrelation times. So, but of course, it would be, I don't know how to do this measurement in this case, I'm sorry. So that would be an interesting thing to do, yeah.
Yeah.
Okay, that was all.
Speaker wants